Hello everyone, I hope you're all healthy and doing well. In today's lecture, we're going to cover section 5.4, properties of the definite integral, which we defined last time. Because we're going to talk about the properties of definite integral, I should first remind you the definition. So recall that a, a continuous function, f on AB is integrable and has a integrable and it has integral I, where this is a real number, if there exists a sequence of partitions a pi with the property that these partitions refine each other, which we defined last time, such that limit of the upper Riemann sums of this function with respect to these partitions is the same as the limit of the lower Riemann sums, okay? And these should be equal to EI, okay? So we defined this last time. So if you have a continuous function on a closed bounded interval, we define, like, given a partition on each partition of the interval, on each subinterval, we have a maximum minimum value of the function because my function is continuous, and we define the upper and lower Riemann sums using these maximum minimum values. So for each partition, I have an upper Riemann sum and a lower Riemann sum, and we said that a function is integrable and it has integral I if there exists a sequence of partitions which refine each other, meaning that each new partition already contains all the previous points. So if there's a sequence of partitions which refine each other and for which the limit of upper Riemann sums and the limit of lower Riemann sums is the same, you say that your function is integrable, okay? So if there's a sequence of partitions which are defining each other for which upper Riemann sums and lower Riemann sums both converge to I, you say that your function is integrable and has integral I. And I told you last time that this condition can actually be dropped, so you don't have to assume that your partitions actually refine each other. This condition can actually be dropped. So I don't have to assume that my partitions define each other. So it suffices for you to find a sequence of partitions for which the upper Riemann sums and lower Riemann sums, they converge to the same real number. So if you can do that, you say that your function is integral and its integral is that number. And using this, we solved an example question. We computed the integral of x cubed over the interval 0, 1, which we found to be 1/4. Anyway, so this was the definition, and I forgot to show this last time, so let me do it right now. There's this math application called GeoGebra, and people are writing applets on this for various like topics. Like this is used for educational purposes, so people are writing these things to illustrate certain notions, and this is an applet written to illustrate the notion of upper and lower Riemann sums. So here's my function here, f of x equals x squared plus 1, and I'm gonna try to integrate this from -2 to +2, okay? And if I use only one interval in my partition, so my partition only consists of 2 points, these two, the area of this big blue rectangle is the upper Riemann sum. The area of the red rectangle is the lower Riemann sum. Now, if I use 3 points here. So if I just partition my interval into two subparts, then again, this will be the upper Riemann sum. The area of this will be the lower Riemann sum. Now let me increase the number of points. So let's use 6 points, which split this interval into a. Okay, I'm using 7 points, which split this interval into subintervals of equal length. And the sum of the areas of these big blue rectangles is the upper Riemann sum, and the sum of the areas of these red rectangles, that's the lower Riemann sum. Now, as you can see, like if I increase the number of n's, the upper Riemann sums and the lower Riemann sums, they seem to converge to a fixed number, which pictorially you see as equal to the area under the graph of this function over the interval -2 to 2. Okay, and this is how we this was the reason we defined the integral in this way in the first place. Okay, so if I increase the number of n's, you see that like the upper Riemann sums and lower Riemann sums, they converge to the same thing. Indeed, this applet already tells you, like, for let's say n equals 30, this is the upper Riemann sum, this is the lower Riemann sum. The actual integral is this thing, and if I increase n, you see that these upper and lower Riemann sums, they start getting closer and closer, and they're approaching to the same number, which is the integral of this function. Okay, so that's that. I just want to show you this. So let's close this. Okay. So some properties of the definite integral. Some properties of the definite integral. Okay, so I'm going to list some properties, and these properties can be proven from the definition, but I'm not going to bother doing that. Okay, the first one is, okay, I'm not going to write down the setting like I have a continuous function and a closed matter interval, blah blah blah. I'm not going to write that down. So the first property is that if I try to integrate any function on the interval AA, so I have a closed interval, but it has no length, like its left hand point and right hand point, they're the same. Okay, so in that case, the integral will be 0. Why? Because remember how we define partitions. We like I have my points x0, xn, and I'm supposed to have these x1, x2, x3 in between these, blah blah blah. If a and b are the same point, then you can't get any non-trivial partitions of that interval. The only partition that you can get is x0 is a, x1 is a. That's it. And in that case, if you try to write down the Riemann sums, you'll see that the delta xi's that we used last time, they become like they are 0. I mean, there's only one xi actually, and it is 0. For this reason, if you try to integrate any function from a to a, the upper Riemann sums and lower Riemann sums will be just 0. And so there are limits, like you can find a sequence of partitions such that this happens. Okay, you use the same partition over and over again. This is 0, this is 0, limit of zeros, the limit of a bunch of zeros is 0, so the integral is 0. So you get that. And the other properties, now this is going to look, I have to explain this. You can actually object to this when you see it for the first time. Yes. Okay. Now we define integral of a continuous function over a closed and bounded interval a, b, where a is less than b. But what if I try to define integral from b to a while assuming that a is still less than b? Now, what you can do in this case is you can actually generalize that definite, like, well, you can really, I shouldn't say generalize, you can extend our definition in the following way. If I give you points a and b, if a is less than b, then you choose partitions like this. But if it's the other way around, and if I'm still trying to define this integral, what you do is you choose your partition so that x1 is over here, x2 is over here, x3 is over here, and so on. You do that. Now, in that case, when you subtract xi plus 1 from xi, you'll get negative numbers, okay? So what's going to happen is, instead of getting the area of a rectangle, you're going to get the negative of that, and so on, and you're going to take the limits of these things. So everything will have a minus sign in front of it, and on that, an extra minus sign. For this reason, if you try to define the integral of a function from b to a, where b is bigger than a, what's going to happen is you're going to get the value of the integral with an extra negative sign. This is why integral of a function f from a to b is the same as negative of the integral of a function from b to a. Okay, so if you extend the definition of a definite integral in such a way that you allow the lower limit of the integral to be bigger than the upper limit, then this will hold. And two more properties, three more properties, I guess. No, actually four more properties. The integral is linear, and what does that mean? It means that if you have constants c1 and c2, well, it suffices for me to write down a plus here, so the minus automatically comes. If you have constants c1 and c2 and functions f and g, the integral of c1 fx plus c2 gx from a to b is the same as c1 times integral of f from a to b plus c2 times integral of g from a to b for constants, for every constant c1, c2. Again, this can be proven via a Riemann-Sum definition, which I'm not going to do. This property is important. The integral of f from a to b can be written as the integral of f from a to c plus the integral of f from c to b for every constant c. Okay, so you can split a definite integral like this. Instead of integrating from a to b, you first integrate from a to c, then c to b. And I'm moving my hands in such a way that I'm implicitly, you may think that I'm implicitly assuming that C is between A and B, but you don't have to assume that. You can take C here. So instead of integrating it from A to B, you can integrate from A to C, then C to B. And because of this property over here, things will work out. Okay, so for any C, instead of integrating from A to B, you integrate from A to C and then C to B. And this can. Okay, so how do you prove that? Well, okay, I'm not gonna, if I start talking about the proofs, I have to write many things down, so I'm just gonna skip the proofs. Let me tell you this. These are not difficult to prove once you actually understand, once you digest the definition of the definite integral. Okay, so you're just gonna take a partition of the interval AC, and then you're gonna take a partition of CB, and then you can observe that when you write down those partitions together will give you a partition from of AB, and then if you have sequences of partitions of AC and CB such that upper and lower Riemann sums converge to the same thing, you combine these partitions, then that will give you a sequence of partitions of AB for which upper and lower Riemann sums converge, so things will work out. So it's not difficult to prove. And this one almost follows from the definition. If f of x is less than or equal to g of x on AB, then the integral of f over AB is less than or equal to the integral of a G over AB. And why? Because if f is less than g on AB, every upper Riemann sum of f will be less than every upper Riemann sum of g, and so on. Like for any, like, well, not. I'm using the same partition. I am sorry. Fix a partition. Compute the upper Riemann sum of f with respect to that. Compute the upper Riemann sum of g with respect to that. If f is less than g, the upper Riemann sum of g will be getting equal to the upper Riemann sum of f with respect to that partition, and the converse thing will happen for the same thing will happen for a lower Riemann sums as well. Okay. So when you take the limits, you will get this. Okay, so this is like a limit of certain Riemann sums. This is the limit of certain Riemann sums. So I'm pretending that f and g are integrable. So this is in particular a limit of upper Riemann sums over a certain partition. Take the same partition, then the upper Riemann sums for that partition will give you the upper Riemann sums will be greater than or equal to these upper Riemann sums. So their limit, if it exists, has to be greater than or equal to this. So you may object that maybe for that sequence of partitions, the limit of upper Riemann sums of G don't exist, but then you can do refinings and so on, which I'm not going to mention, and get this. I mean, okay, if I'm not going to prove these, why am I talking about their proofs? Like, well, the point is, these are not difficult to prove if you want to prove these, okay? So, and finally, I have the triangle inequality for integrals, which tells you that the absolute value of the integral of f over AB is less than or equal to the integral of the absolute value of f over AB. Okay? So, let me write that down. Let fg be integrable on an interval on a closed interval containing the points A, B, C. Okay, so this is my setting. Like, in order to be able to write these down, in order for these to make sense at all, I need to assume that all these things are integrable. So I wrote that down. The point is, like, these properties are I'm not going to say easy to prove from the definition. They're not difficult to prove. Okay, so if you're curious about the proofs, you can try proving these. Otherwise, you can send me an email and I'll sketch you a proof. Okay, so that's that. Now, before we move on to the mean value theorem for integrals, let me solve a couple of questions. Okay. Okay. So let's solve this. Show that the integral of a to the power minus x cubed from 0 to 1 is between a 3/4 and 1. Okay. Okay. Now, we haven't learned about fundamental theorem of calculus, so those who know how to integrate properly with fundamental theorem of calculus may like ignore what I'm going to do in the solution and say that, okay, I can actually integrate this without Riemann sums. Well, you actually can't. You can't find an antiderivative of this function written in terms of what people call elementary functions. So you won't be able to integrate this using fundamental theorem of calculus. I mean, I think it may be done, like you can express an antiderivative of this function in terms of some special function, so it can be done I guess with the usual method which employs the fundamentals of calculus, but let's just say you won't be able to do it. So how are we going to show that this integral is between these numbers? Now, what I'm going to do is I'm going to try to use Riemann sums, but the problem is if I try to use Riemann sums, I have to evaluate this function at certain points, and it's not easy to evaluate the exponential function at certain points. For example, can you evaluate this function at a 1/2? What do you get? E to the power minus 1 over 8. Does anyone know what e to the power minus 1 over 8 is? I'm going to add these up, and I'm going to compare this with 3/4 and 1. So you may also think at the moment that maybe we can prove this via Riemann sums, but it seems as if that approach won't work as well. Well, that approach may work if you actually be smart and tweak what you're doing a little bit. How? Now, here's a general fact. A exercise for the reader. Show that e to the power t is greater than or equal to 1 plus t for all t, okay? So you can show that e to the power t is greater than or equal to 1 plus t for all t. How can you show that? Well, just do this. Just do the following. Call your f of t e to the power t minus 1 minus t. Show that this function is decreasing on the interval minus infinity to 0, and it's increasing on the interval 0 to infinity, and its value at 0 is 0. So the lowest it can get is 0, which means that this is greater than or equal to 0 all the time, which means that e to the power t is greater than or equal to 1 plus t. So you can do that and pretend that you showed this. Then we have that this integrand e to the power minus x cubed is between so instead of t I'm going to write 1 minus x cubed, and on the interval 0 1 the largest value of this thing is 1, okay, because this is like a decreasing function and its largest value is obtained at 0, and at 0 it takes the value 1. So for all x in the interval 0 1 I have this inequality. Therefore by this property of the definite integral I have that the integral of 1 minus x cubed over 0 1 is equal to the integral of e to the power minus x cubed from 0 to 1. This is equal to integral of 1 over the interval 0 1. And so now this integral I can actually well, let me use the linearity of the integral over here to split it like this, and then this is what I'm gonna get. Now, if you compute the integral of any constant function over an interval, what you're going to get is, because your function is constant, your upper Riemann sums and lower Riemann sums, it will, like for any partition, you will get the exact same upper Riemann sum and you will get the exact same lower Riemann sum, which will be the value of your constant function times the length of the interval. So over here you're going to get over here you're going to get a 1 as the integral, and this will be 1. and we have computed the integral of x cubed over 0 1, and we found it as a 1 over 4. So I have that 1 minus 1 over 4 is less than or equal to this integral, and this is less than or equal to 1. Okay, so we've computed this before, computed last time using Riemann sums. I know this might be boring for you, like you know that we're going to develop a very powerful tool to evaluate these definite integrals, but I just keep using Riemann sums to solve my questions. Well, that's because the fundamental of calculus is in section 5.5, so we're going to learn about it in the next video. So for this video, we're going to stick to Riemann sums. So that's that. Let me solve another question. So what did we do here? We wanted to find an upper bound and lower bound for a certain definite integral. At first, I thought that maybe I should use Riemann sums, but then, like, computing the Riemann sums for this function would be difficult. So what I did is I estimated that, using the previous techniques that I've learned. I've said that, okay, this function is greater than or equal to 1 plus t, so its integral is greater than or equal to the integral of 1 plus t. So I need to integrate 1 plus t, and the Riemann sums are easy to compute for 1 plus t, or like if you put here instead of t we put x cubed. So the Riemann sums for this is for this term is easy. Okay, we actually computed them last time. Like we've computed the integral of x cubed over 0 1 using Riemann sums. So we use that, and result follows. So I should not waste your time with this simple example. I should solve more examples. Okay, so here's another question that I want to solve. Okay, let f be continuous and decreasing on the interval, let's say 0, 3. Suppose that f of 0 is 10, f of 1 is 8, f of 2 is 6, and f of 3 is 4. So the question is, show that the integral of this function over this interval is between 6 and 8. I hope my values are right. We'll see. So this is a very similar to a question that we actually asked a couple years ago, maybe 2 years ago. So let's understand what's going on. So I have a function which is continuous and decreasing on the interval 0 to 3. So this is my coordinate axis, and I have a function which is continuous and decreasing. That's going to be important on 0, 3. Okay. Now, I'm given its values. Its value at 0 is 10. Its value at 1 is 8. Its value at 2 is 6. And its value at 3 is 4. Okay. I'm asked to prove an inequality regarding the integral of this function. Now, and this is a continuous decreasing function. Now, how can I approach to this question? What students tend to do is we give them some data, and they basically fill in the data by what's convenient to them. For example, sometimes students just like to do this. Okay, I'm just going to pretend that my function looks like a line, like this. And then I'm going to compute the integral for this, for which I am going to get a... This is off. This is very off, not 6 and 8. I am sorry for this. 18 and 24. Okay, I had some other numbers here. I'm sorry for that. I'm sorry for that. Anyway, what was I talking about? Okay, sometimes students just do this. Okay, I'm gonna pretend that I have a line here, and then I get this trapezoidus area is what? 4 here, 10 here, 7 times 3, 21. So I proved that 21 is between 18 and 24. Well, I am not asking you to show this inequality for that function that you chose, which was chosen by you only because you want to work with that. I want you to show that this inequality is true for every function satisfying these, for every decreasing continuous function for which I have these values. So you can't simply choose your own function. You have to pretend that f is any function which satisfies these properties. Okay. So how are you going to approach to this? Well, let's think about this. Okay. I'm going to have a function which is continuous and decreasing, and it's going to decrease from here to here. What can happen? It can look like this. Okay. It can look like that. Okay. So let's say that I can't choose my function, but pretend I can't choose my function. I want to have a definite integral which is as large as possible over this interval. What would I do? I would choose my function like this. It goes like that, and then it decreases like this. It goes like this, it decreases like that. Okay, so this would be continuous, and the integral of this would be very close to 24 if you actually compute that. Okay, and if I want to write that, like if I had the ability to choose the function, which I don't, how would I guarantee that its integral is as small as possible? It's supposed to be continuous and decreasing. Then I would choose such a function. Okay, I would do something like this. You see, I can't do that because my function is decreasing. Okay, now I'm going to use as I said, like if I could choose my functions, I would choose them like that in order to maximize and minimize the definite integral, but I can't. So what am I going to do? I can use the ideas that I have just illustrated. What ideas? You see, this function is continuous and decreasing, and its value at 1 is 8, which means that its value at over the interval 0, 1 is at least 8 all the time because it's decreasing. Like it's decreasing to 8, which means that all its value is greater than or equal to 8 all the time. And because it's decreasing and its value at 0 is 10, the values are bounded above by 10. They can't exceed 10. And similarly, on the interval 1 to 2, the largest possible value of my function is 8, and the smallest possible value of my function is 6. And over here, this is the largest possible value, and this is the smallest possible value. Okay, now as f is decreasing on 0, 3, if I choose the partition 0, 1, 2, 3, if I choose a partition of this interval which splits this interval into 3 equal pieces, the upper Riemann sum of f over with respect to this partition will be, well, I take the maximum value of the function over this interval and multiply that with the length of that interval. and I take the largest value of my function over this interval, which is 8, and I multiply it with the length of this interval, and I do the exact same thing for the last one. I take the largest possible value of my function, which is 6, and I multiply it with the width of this interval. So this is going to be my upper Riemann sum, which is going to be 24. And my lower Riemann sum is going to be the least possible value of the function over this interval, which is 8 times the width of this interval, plus least possible value of the function over this interval, 6 plus 6 times the length, and similarly I have 4 times the length, and I'm going to have 18 over here. So this is like maximum of, I already explained this in words, but I should also write this down, because some of you will simply print these notes and not bother watching the videos. So this 8 is like the maximum value of f over the interval 0, 1, and this is the length of the interval 0, 1, and this is the this is like the min, not max, this is the min. And let me also write these down. This is the max of f over the interval 0, 1, and this is the width. Okay. Okay. Now, thus, remember, you have your integral, you have your upper Riemann sums converging to this, lower Riemann sums converging to this, and we have the following general fact. An upper Riemann sum for any partition, an upper Riemann sum is always greater than or equal to your integral, which is always greater than or equal to a lower sum. So, by definition of the integral, we have that the lower Riemann sum of f with respect to this partition is greater less than or equal to the integral, and that's less than or equal to the upper Riemann sum of f with respect to this partition. So this is, we proved that like we showed that this is 18 and this is 24, and that's it. I have shown that this integral is between 18 and 24. Okay. Now let me solve one more question, and then we're going to talk about the mean value theorem for integrals. Let f of x be given by the following rule. So if x is between -2 and √3, it is 4 minus x squared. You can check that for x values in this interval, this is 4 minus x squared is non-negative, so this is defined. And for x values between √3 and 3, my function is minus x plus √3 plus 1. So the question is, find the integral of this function from -2 to 3. Okay. First of all, in order to talk about the integral of this function over this interval, at the moment I haven't talked about piecewise continuous functions, so at the moment I should just check whether this function is continuous or not over this interval, and you can actually check that it is continuous. Okay. So how are we going to find this integral? Well, let me draw Okay, this is not what I want. Let's use that. Let's use this. Let me roughly sketch the graph of this. Okay. Now, this is the upper part of the circle centered at that's something's off. I'm gonna check my numbers. I keep No, this is fine actually. No, this is fine. This is the upper part of the circle centered at the origin with radius 2. So this is the upper semicircle centered at origin with radius 2, and like y equals that, y equals squared 4 minus x squared is that. So my function looks like a semicircle from the point minus 2 up to the point root 3, okay? And then starting from root 3 up to 3, it looks like it's going to be a line. Y equals minus x plus root 3 plus 1. It's going to be a line, okay? And it's going to be a line, and at point 3, like the graph of my function will be a line over here, and at point 3, its value is a root 3 minus 2, okay? So you can check that. Okay, and let me also find this point. When you set this to 0, you'll see that x is root 3 plus 1. So at the point root 3 plus 1, the value of my function is 0, okay? Now, this is a continuous function, okay? The right limit of this at root 3 is 1. The left limit of this at root 3 is 1. The value of the function at root 3 is 1, so this is continuous. I should actually delete one of these inequalities. Okay. Now, I'm asked to find the integral. The integral of this function, I can write this integral as a sum of 3 separate integrals. Okay, integral of f from minus 2 to root 3, integral of f from root 3 to root 3 plus 1, and integral of f from root 3 plus 1 to 3. And by the geometric interpretation of integral, I know that this will be, like the first integral will be the area of this region, okay? So I need to find that area. How am I going to find that area? Let me draw it over here. So I have a semi-disk, and this is 2, this is root 3, and this is 2. Okay, so this is 2 root 3 2. So by Pythagorean theorem, this is 1, which means that this is 30 degrees. So this is pi over 6, which means that this is 5 pi over 6. This angle is 5 pi over 6 radians, which means that this yellow region has area. Let's compute this. The full disk with radius 2 would have area pi times 2 squared. I am taking if I took the full disk, this would be the area, but I'm not taking I'm only taking a portion of it, like how much of it am I taking? A 5 pi over 6 over 2 pi of it. Okay, so I'm taking 5 pi over 6 over 2 pi of it. Okay, and then this is the area of this region, and then the area of this other the area of this triangle is the area of that triangle is a the area of the triangle is 1 times root 3 divided by 2. So this is the area of the yellow region, and then I will have the integral of f over this interval will be the area of this blue region. So this is like this is a triangle, and this is the point 1, and this is 1. So the area of the blue triangle will be 1 times 1 divided by 2. And over here, I have another triangle. And this time, this length is 3 minus this, 2 minus root 3. So the area of this region is 2 minus root 3 times, this is very thick, so let's make it thinner. So I have 2 minus root, this is very thin now. I'm going to use this one. Okay, 2 minus root 3 times the height is 2 minus root 3. The height is 2 minus root 3 as well. So 2 minus root 3, and I divide this by 2. So this is the area of this region. However, you should be careful. Remember the geometric interpretation of integral. It gives you the signed area between the graph of function and the x-axis. And when I talk about signed area, what you should do is, when computing areas, signed areas, if your region is above the x-axis, its signed area is its actual area. If it's below the x-axis, its signed area is negative of its actual area. So the signed area of this region would be minus that, okay? And this is the integral, okay? So this is the integral of this function over this interval. So let's see, we solved 3 questions. This one basically uses one of these properties, namely if f is less than g, integral of f is less than integral of g. And this one illustrates, like this one's about Riemann sums. It's a nice question, so that's that. And this one is about the geometric interpretation of the integral. So I think at this point we can start solving questions and start talking about the mean value theorem for integrals, which is something important, okay? Because we're going to be using this to prove the fundamental theorem of calculus, okay? So the mean value theorem for integrals, okay? So let f be continuous on the interval AB, okay? Then there exists a number C between A and B such that f of C is equal to the integral f of C is equal to the integral of f over AB divided by B minus A. Okay? So Let me first prove this, then we're going to talk about why this is called the mean value theorem for integrals and what this means geometrically. Well, what this means geometrically, you will see it actually in the proof, okay? So, by the min-max theorem, f attains its maximum, its absolute maximum and minimum values a on AB, say m and little m respectively. Okay, now okay, remember the I just I'm kind of tired, so I don't know how many seconds has this since I didn't speak. So remember that because f is a continuous function on a closed and bounded interval, it has its absolute maximum and it has its absolute minimum at certain points. Let's call the absolute maximum value, not the point where it is attained, but the value, the maximum possibility of f, big M. And let's call the absolute minimum value small m. Then for the partition PAB, from the partition PAB, we get that. Now, let me use the partition of the interval AB, which only consists of the points A and B. So I don't actually part anything. Like my partition consists of a single big interval. It's AB. I only have 2 points. Now, if you compute the lower Riemann sum of a f with respect to this partition, you're supposed to do what? You're supposed to take the minimum value of f over this over each interval, multiply with the width and so on, but there's only one interval and it's AB, so I need to take the minimum value of f over AB, which is little m, and I need to multiply this with the length of the interval, which is b minus a. And I know that any lower Riemann sum is less than or equal to the integral, and any the integral is less than or equal to any upper Riemann sum. Now, if you compute the upper Riemann sum of f with respect to this partition, you're going to get m times BA. And so we get that this quantity, integral of f over AB divided by b minus a, this is between a big M and small m. Since f is continuous, now this is almost by definition of the integral. Like the definition of integral automatically forces you to have the following inequality. The integral is less than or equal to any upper Riemann sum, is greater than or equal to any lower Riemann sum. And by dividing both sides to b minus a, you get that m is this number is between small n and big M. Now, f is continuous, and the intermediate value theorem tells you at this point the following: I have a function on some closed interval AB. This is its maximum value. This is minimum value. Big M, small m. I take some number, namely this number, which is in between. By the intermediate value theorem, there exists a point for which the value of my function is exactly this, okay? So by the intermediate value theorem, there exists a point C between A and B such that a f of c is this number. Okay, and that's it. We have finished the proof. Okay. Okay. So this little box, mathematicians put these to indicate that the proofs are complete. It stands for a QED, which in Latin is a quad. Okay, I'm not gonna attempt saying it because I'm gonna make a fool of myself, and I don't want that, at least not in front of the camera. So my Latin is not that good. So that's that. Now let me tell you what this means geometrically. What this means geometrically is, like, what this term tells you geometrically is this. You have your function, and this is your, let's say this is the graph of your function, and these are a and b. What this function says is this: you compute your f, you compute the integral of your f from a to b. So you find the signed area of this region. Okay, you find the signed area of this region. And then you divide this to b minus a. Okay. There is a point in this interval a b such that the value of the function at that point is that number. Now, so let me write that down. Pretend that this is that. Now, if I were to draw this a rectangle, what would its area be? It would be the height times the width. So it would be this term multiplied. I said divided. I am sorry. The area of this would be the height times the width. So what would it be? It's this number times b minus a. So that would be the integral. So the point is, the area of this yellow rectangle is equal to the integral of f from a to b. So what it tells you is that, like, if you have your function, if you have the graph of your function, if you compute the integral, which gives you geometrically this the signed area under this curve over AB, you can actually find a point for which, if you just draw this rectangle, you will get the same area. Okay. Now, let's try to understand what this means, maybe using an example from physics. Pretend that this is like f tells me the velocity of a moving particle at time x. Then this would be display, like the integral of that would be what? The displacement. Okay. And the displacement divided by the total duration of travel would give me the average velocity. Okay, so this number is my average velocity, and this like, if you try to interpret this Memel theorem for integrals in terms of velocities and displacements, then what you get is this simply tells you that at some point during your travel you have to achieve your average velocity. Okay, so it says that. And the reason it's called the mean value theorem is, well, this quantity is the mean average value of f. It's called the average value of f over the interval AB. So I'm going to write that down. Okay, I did something bad. That's that. So let me write that definition down, and then I think after that we're going to stop. Yeah. This quantity, the number integral of f from a to b divided by b minus a is called the average, in other words, mean value of f over the interval AB. Okay? This is why this is called the mean value theorem for integrals. This simply tells you that if you have a continuous function on a closed unbounded interval, its mean value is actually attained somewhere. Okay. So that's that. And let's move on. And I'm gonna write down one more definition, and then we're gonna stop. Okay. The last definition of this section, the integral of the definite integral of piecewise continuous functions. Piecewise continuous functions. Okay. So suppose that a function f is piecewise continuous. Now I'm gonna have to define this. Piecewise continuous on the interval AB. Now, piecewise continuous simply means the following. That is, there are points a equals C0 less than C1 less than C2 less than that Cn, which is equal to B, such that f is continuous on each ci plus 1 open interval. Okay. Suppose that blah blah blah. Then, so what this means pictorially is this: piecewise continuous on an interval simply means that your function is not necessarily continuous, but you can split your interval into subintervals so that on each of these intervals, like if you just restrict your attention to those intervals, you get something continuous. Okay, so the restriction of your function to those the restrictions of your functions to those intervals are continuous. So it's piecewise continuous if you can find points C0, C0, C1, C2, C3, dot Cn, such that on each open interval, you see, I want to erase this. I am sorry. On each open interval, my function is continuous. You see, I'm not saying that my function has to be continuous on the closed interval ci plus 1. I want to be continuous on the open interval. So I don't care what happens at the endpoints of these intervals. So piecewise continuous means this. If your function is piecewise continuous on an interval AB, that means that you can just split AB into subintervals so that inside each interval, meaning that like in the corresponding open intervals, you have continuous functions. You don't care what happens at the endpoints. Well, I don't actually want that. This is wrong. This is wrong. Because I don't actually want my function to go up to infinity like this. Like if I use this definition, a function which goes like this, and maybe at this point is defined like that, this would also be piecewise continuous. I don't want that. I'm just going to modify this definition. Okay, there are points blah blah such that a f is equal to a f of I for some on ci plus 1 for some continuous function fi on the closed interval ci plus 1. I think this is what I want. Yes. I am sorry for the mistake. So piecewise continuous means this. You split your interval into subintervals, and on each subinterval, on the corresponding open interval, your function is identically the same as a continuous function, which is continuous on the corresponding closed interval. Now, if you take this definition, this prevents such things. So such a function would not be piecewise continuous. Okay, it goes to infinity like this, and maybe its value over here is here. So this is not going to be piecewise continuous, because you can't find some function fi which agrees with this function on this closed interval. Okay, so you can't do that. So a prototypical piecewise continuous function looks like this. Okay, so you have these subpieces. On each subpiece, on the corresponding open interval, your function behaves like a continuous function, which is continuous which can be extended to a continuous function on the closed interval. Okay, so that's that. Now, if you have this, then the definition of the definite integral of f over ab is done like this. Then we define the integral of f from a to b as the sum of integrals of these continuous functions. So what this geometrically means is, like, if you want to define the integral of this piecewise continuous function f from a to b, then you just you know that for this on this interval c0 c1 there is some continuous function which agrees with f, and take the integral of that. Okay, take the integral of that. So take the integral of that, and then for this one there is a corresponding f1, and take the integral of that from c1 to c2. Take the integral of that function and take these integrals and add them up. Okay, so that's that. This is how we define integral of piecewise continuous functions. You see, I can't use the Riemann sum definition because in the Riemann sum definition, in order for me to talk about the maximum and minimum over an interval, I need to know that those exist, but we don't know a theorem which guarantees the existence of maximum and minimum values over closed intervals, which doesn't require my function to be continuous. I mean, you can come up with such theorems. Well, actually, can't in general, but the point is that definition won't make sense for piecewise continuous functions, because when you try to take the maximum value of your function over a closed interval, because it's just piecewise continuous, that maximum may not exist. Okay, so it may look like this. Maybe you're maybe in the partition you get this interval, then you try to take the maximum of your function on over this interval, but the maximum doesn't exist. Okay. So the point is, for piecewise continuous functions, the usual Riemann sum definition of integral won't work. So what we do is, because piecewise continuity means that you can split your interval into subintervals, so that on each interval your function is identically the same as a continuous function, which is actually defined on the corresponding closed interval. So what you do is you just take the definite integral of those continuous functions on those closed intervals, you add those up. Okay. So that's that, and I think I'm gonna stop. I am sorry for that little mistake, which I am not going to edit out from the video. By the way, it's just gonna stay there. Well, I fixed it. So. I'm not going to solve any questions about this. I don't think it's required. What we're going to do next is we're going to learn unarguably the most important theorem of this specific course, which is the fundamental theorem of calculus, to which everything coming after will depend on. Okay, so stay safe and expect more videos. Good day.